Now only 18 of you. Hopefully the rest will be joining soon. All right, so let's continue with energy gap. But before we continue, let's do some recap on what we've learned in the previous lecture, right? So usually, before we move to the next topic, I'll do this section at the very end of the lecture, which is what I call challenge what you've learned. So that you can recap on what you've learned in the previous topic. Okay, so we have discussed question 1 yesterday, and then we have discussed question 2 yesterday as well during the beginning of the lecture. So let's just go through question number 3 and 4 today, right? So before we move on to energy gap, so let's go to question number 3 now. Why do we need to dope semiconductor materials? Okay, anyone? Why do we need to dope semiconductor materials? What are you looking for? Anyone? You can unmute yourself. You can write down in the chat box as well. Why dope? Right, to alter conductivity, to alter the conductivity or resistivity of a semiconductor, yes. All right, to increase conductivity, yes. Conductivity, yeah, that's close. All right, good. Need to increase the conductivity with less energy required, yes. All right, okay. So the essence is to alter the conductivity or resistivity, if you like. The inverse of it is resistivity of the semiconductor in order to produce what we want to get, for example, right? So depending on the requirement of the semiconductor devices that you're going to work on, okay? Some conditions you may need to work on intrinsic, which is undoped silicon. In most conditions, you need to dope the silicon to certain levels, right? So it can be lightly doped, it can be moderately doped, it can be heavily doped, it can be a combination of the 2 or the 3, depending on the device architecture. So it's clear now. So then question number 4, how do we do that? How do you dope the semiconductor material? We've discussed briefly yesterday. Right, dope with trivalent or pentavalent element, yes. In the process that's called diffusion, yes, good, yep. All right, so when you mention, say, in this case, since in this course we are referring a lot to silicon, so you can just assume that the host atom is silicon, and therefore, when the host atom is silicon, you can just assume that the dopant will either be from trivalent group 3 or pentavalent group 5, right? But when it comes to other semiconductor materials, you really have to specify the origin of the dopant, right? The column of the dopant as far as the periodic table is concerned. But for this particular course, it's understood that the host atom is silicon, and therefore we're only talking about group 3 or group 5. Okay. And the process is called diffusion, yes. So how do we do the diffusion? What are the processes involved briefly? We have not covered the detailed process in this course, but at least we've discussed some basics of the processes on how do you actually do the diffusion process. Anyone who'd like to share how to actually do the process? How do you actually incorporate the atoms? Najia, would you like to elaborate on the diffusion process? a bit. How do you run the process? What are the typical parameters or settings? How about the temperature? All right, and the diffusion movement of impurity atoms in a semiconductor material at high temperature. Yes, you want to movement of impurity atoms. In this case, is you want to drive the impurities into the silicon. Okay, you want to drive the impurities into the silicon. So that means it can either be done through high temperature diffusion process, 900 to 1000 degrees C, as stated here. Yeah, 900 to 1000 degrees Celsius. It can be done in the furnace. It can also be done by spin coating process, and then you send the wafers to the furnace to do the very same thing. So the whole idea of that process is you have to incorporate the dopant to the surface. Or let me just get my wafers. So I'm in the office right now. I can show you. If you have not seen a wafer before. I have a couple now. I can show you a couple of wafers. Let me show you the wafer. If you've not seen any wafers before, this is an example of a silicon wafer, 2-inch, 2-inch. So let me put right in front of the camera so they can see. So this is 2-inch in diameter. So that's about 5 cm across. So this is okay, right? Okay, you can see that. So this is 2-inch silicon wafer. The lines on the wafer are metal contacts. You can evaporate the metals on the silicon wafer for you to use for, say, photo detectors, for example. One of the semiconductor devices that you will learn in the second half of the course. So this is just a 2-inch. I believe it's P100, P100, P-type 100, right? So I'll show you another example as well. This is a bigger one. Since I'm in the office right now, I have a solar cell based on silicon to show you. So this is a 5-inch silicon wafer, very thin one. Can you see on the screen? You can see, right? So this is 5-inch across. So 5-inch silicon. Tapi dia, well, the blue color here is from silicon nitride deposited on the silicon in order to anti-reflect the light. Yeah, very opaque, exactly. So the thickness here, if I can show you the cross section, is very, very thin. It's about 180 micron. So that's about twice of our hair thickness. And it's very brittle. So the moment I bought this silicon wafer first time, I didn't really know how to handle 180 micron with the force of my hand. So I broke the first one. Because it's too brittle. Kalau you terlepas di atas meja, then it'll just break because it's too brittle. It's just, you have to really handle with care. That's 5-inch, right? So it's silicon wafer coated, the blue color is coated with silicon nitride, about 75 nanometer, as an anti-reflection layer for solar cell. And then those lines, those vertical lines are silver lines, silver bus bars. And you cannot see here, there are also horizontal lines, small one, very small one, about 150 micron or so in the width, right across horizontally, yeah. Yang tu dia lagi kecil daripada bus bar. Bus bar ni is bigger because it's there to collect bigger current, larger current. So ada metal line yang horizontally distributed on the silicon to extract the carriers, electrons in this case, in a smaller channel before the electrons go to the bus bar to be collected. Dia macam the horizontal lines here are like smaller roads, if you like, jalan kecil ya, maksudnya elektron tu keluar dekat jalan kecil, kemudian dia masuk dekat banyak-banyak elektron masuk dekat jalan besar, dekat highway. So the bus bar is like the highways, and the metal lines here, the horizontal part is like the small roads. Yeah, so the silicon wafer include HTL, ETL, top and bottom contact. Yes, you can see here. So it is not called HTL and ETL in this case. Whole transport layer, electron transport layer is not used in this particular case because the HTL and ETL are used mostly for organic solar cells and perovskite solar cells. But for this particular case, the silicon solar cell, we normally call silver front contact. And let me just flip. You can see, right, the lines at the back. So those lines are aluminum rear contact. So if you do like that, later on when you learn about p-n junction, you're gonna learn that this silicon wafer is p-type, and then on the very thin surface, the first 200, 300 nanometer of this silicon wafer is n-type, diffused with phosphorus, and then on top of the phosphorus, on top of the n-type layer, we evaporated silver contact, silver there, and then at the back there, okay, is aluminum contact. So this aluminum is in contact with p-type wafer. Yeah, tak nampak. Let me just get to the camera again. All right, okay. So this aluminum is in contact with p-type silicon wafer, and this silver front, yeah. So this silver front contact is in contact with the n-type. So silver is in contact with n-type, aluminum is in contact with p-type, and you have p-n junction in between. So then you complete your junction, and the carrier extraction will take place through the contacts, the front and the rear contact. Okay. Yeah, so that's a very good example. Okay, so clear. Sekarang you dah nampak kan how does a p-n junction in a silicon looks like. Walaupun it's not physical junction, but then the fact that one contact is connected to one polarity, like silver on the end, and then the other one is connected to the other polarity, like in this case, aluminum on the P. So that, and then you have your p-n junction in between. So your P is here, your N is here, and then your front is silver, and then your rear is aluminum, then you complete your p-n junction. So that's basically already a solar cell. So it's a matter of how good is the performance of the solar cell, right? Good, right. So let's move on to energy gap. So in this lecture, you're going to learn about a couple of important things related to energy gap. The first one is band structure of a crystal, and then the concept of band gap, and then effective mass of electrons and holes, which we are going to use a lot in the calculations of related to this later on. We're going to do some exercise, including in your assignment 1. And then we're going to review band diagram, EK diagram, call it, where you have your energy axis on the Y and then your K on the X. And then we're going to look at the concept of direct and indirect band gaps. What do they mean? The conduction in metals, semiconductor and insulators, and temperature and doping dependence of band gap. So that means in this case, the band gap can be altered depending on the temperature and doping conditions, right? So that can be customized if you like. So the band structure, so just move this a little bit. So the band structure of a given material is shown as below. You can see metal in the A and B, and then semiconductor in C, and then insulator in D. And we've discussed this one briefly as far as the gap is concerned, right? So we still need to find out which energy levels are occupied and whether specific bands are empty or partially filled or completely filled. So these are the situations that you have to consider when discussing about the band structure of a crystal. So empty bands do not contain electrons and therefore do not contribute to electrical conductivity of the material. So for example, if in equilibrium condition, your valence electrons are tightly bounded, then there's no room for conduction unless there's always an unless the operating temperature at that particular condition allows for the electron hole pairs to be generated, or electron hole pairs unless the bonds are broken, right? The bonds are broken by thermal component or thermal excitation, we call it, right? So in essence, even though the valence electrons are tightly bounded, but if you increase temperature to X temperature, say, that temperature can actually cause thermal excitation of your valence electron into the conduction band. And in that particular moment, your valence electrons will become free for conduction, even though earlier on they are tightly bounded, okay? So what is partially filled bands? Partially filled bands, you can refer to A and B here, contains electron as well as an unoccupied energy level, which have slightly higher energy. Then unoccupied energy level enable carriers to gain energy when move in an electric field, if there is an electric field. But if there is no electric field, they cannot move. Therefore, electrons in a partially filled band do contribute to the electrical conductivity of the material if there is electric field surrounding the material, right? And this occurs in materials with only one valence electron, for example, sodium and potassium, Na and K, okay? So these two elements fall into this partially filled band condition. So these materials are conductive even though the bands do not overlap as in B. So as in A, even though it's partially filled, but due to the single valence electron, they can actually move and contribute to the conduction. Even though in the previous class we discussed that metals have completely overlap band between valence and conduction band, okay? So on the other hand, when you talk about completely filled bands, these contain plenty of electrons but do not contribute to conductivity of the material if there is no free electrons available, right? So next we move to band gap. What is band gap? We've discussed briefly. Band gap is essentially the space or the forbidden gap between the valence band H. Valence band is the whole thing down here. Conduction band is the whole thing up here. Let me just check. Can you see my cursor? Can you see my cursor moving? Okay, good. Okay, because I forgot to bring my my stylus today. Right, so the whole thing up here is conduction band, the whole thing down here is valence band, and then band gap is the space between the valence band H, the maximum energy level of the valence band, to the minimum energy level in the conduction band, and the space in between is called band gap, right, or the forbidden gap. So band gap is, you can relate this to energy required to excite an electron from VB to CB. So assuming that your valence electrons are sitting at the edge or close to the edge of the valence band, to be able to get to the conduction band, the valence electrons need to be excited by applying enough energy, and that energy is equal to band gap, right? So if you're talking about 1.12 electron volt for crystalline silicon, so that means in order for you to excite valence electrons from the silicon, the crystalline silicon, you have to supply at least 1.12 electron volt energy in order to excite the valence electrons, or else they won't be excited, right? If you supply, say, 1.0, they won't be excited. If you supply 0.6, they won't be excited, because you need to overcome that barrier, which is equal to 1.12 for crystalline silicon. You have to be careful when you mention silicon in general, because silicon in general may mean crystalline silicon, which has a band gap 1.2 electron volt, or it may mean amorphous silicon as well. Amorphous silicon, on the other hand, has a band gap of 1.8 electron volts, right? So when you mention silicon, unless it's understood by all the audience, then you can say that it's silicon, which means crystalline silicon. Or if you want to be more specific, it can either be crystalline silicon or amorphous silicon, okay? Because the band gap are different to begin with. Nanti akan takut ada confusion lah. So remember 1.8 EV for amorphous silicon, 1.12 for crystalline silicon. And for multicrystalline and for monocrystalline, both have the same band gap, 1.12. Okay, amorphous je lain. Mono and multi sama, mono and multi/poly sama. So result from the properties of the material based upon its atomic structure, and atomic properties. We're going to see later on. So the band gap is produced by the properties of the atomic structure and the atomic properties of material. So band gap, if you want to relate to the wavelength, or if you want to convert to the wavelength, you can always use this in online calculator available on Google search. So the wavelength is equal to 1.24 over Eg, right? So Eg is equal to 1.24 over lambda. So vice versa. Okay, so the regular structure, for example, crystalline lattice, is a principal factor in determining the properties of the semiconductor material. So mechanical, electronic. So the properties of the semiconductor really depends on the crystallinity and other factors of the semiconductor material. So what you can measure is the mechanical, electronic properties, but the determining factors is actually the inside of the lattice, the properties of material itself. So we have been mentioning a lot on 1 electron volt, 2 electron volt, 3 electron volt, whatever. So what is 1 electron volt? So 1 electron volt equals to 1.6 times 10 to the 19 minus 19 joule, which is an electronic charge, but converted into joule. But as far as the definition of 1 EV is concerned, it is actually the energy gain. So it's the amount of energy gained by 1 electron with electron charge of 1.6 times 10 to the minus 19 coulomb as it falls through a potential of 1 volt. So just imagine this electron, for example, if it falls through this barrier with a potential of 1 volt, the energy involved during the transition is equal to 1 electron volt, right? So the same goes to the reverse process. If you're saying that it's going to be excited from the lower potential to higher potential, then it has to gain, it has to get the inverse process of the same amount, 1 EV. So what causes the band gap? So when you bring, you can say, you can always discuss this in the form of atom, for example, silicon atom or whatever atom, semiconductor materials. But when you bring all the atoms together in a solid, in a semiconductor material as a bulk together, right? Trillions perhaps of atoms are brought together. So when they're brought together, they will create a solid or the bulk, and they interact with each other, the atoms. As a result of this, the balancing forces will create lattice space in the bulk, right? And the interaction between the atoms brought together closely will result in interaction wave functions of electrons. And the interactions between these atoms brought together will define the electrical properties of the resulting solid, for example. So if you can see this graph down here, you can see electron energy on the y-axis and the interatomic spacing or distance on the x. If you reduce the x, okay, dia punya energy tu dia akan ada interaction between the neighboring atoms coming together, and you can see the smearing of the energy, right? The smearing of the energy forming gaps, forming energy gaps. So the energy momentum relationship for a free parabolic, free electrons parabolic, you have learned this in 307, and that's given by this equation. So when the electron is moving within the periodic crystal, as what you learned before, the atoms of the lattice affect the electron's motion, and therefore this graph. So it becomes discontinuous with some energy levels becoming forbidden, just like what you saw on this graph, right? When they're brought very close together, you're going to see discontinuity with some energy level becoming forbidden, which forms the band gaps, right? So this is another representation of details. You can also see this from different discontinuous bands, okay? So the presence of the structure, periodic structure of the lattice, so when they're brought together, they form some sort of crystal, changes the velocity and effective mass of electrons and holes. So these values of effective mass of electrons and holes will be used a lot when we do density of states calculation, which we'll cover later on in the next topic, DOS calculations, and then conductivity calculations, right? So for example, if you pick silicon, right? Silicon with a band gap of 1.12 eV at room temperature, about 300 Kelvin, and then you're gonna be using, for example, electron effective mass of 1.08 for DOS calculation, and then on the other hand, for conductivity calculation, you're going to be required to use 0.26, right, due to the origin of the calculation. So you need to use the right values for the right calculations. So band diagram. Band diagram is a simplified representation of the energy structure of semiconductors such as silicon or germanium or whatever, right? So essentially, you have to be able to represent the conditions or whatever condition you're discussing in the form of this diagram, energy on the Y, and then the space on the X, and then with valence band and conduction band, and then the separation between both, which is the band gap, right? So for example, if you look at T0 Kelvin, right, at T0 Kelvin on the left, all valence electrons reside in the VB. So they are all tightly bounded in the VB. And then the CB is completely empty of valence electrons. And there is no electrons, there's no free electrons in the CB to do the conduction at 0 Kelvin. On the other hand, if you increase the temperature to higher than 0 Kelvin gradually, depending on the temperature, to be exact, you're going to have occasional phonon from lattice heat, which gives this higher temperature, the gradual increment of the high temperature will contribute to the lattice heat, which will then give enough energy to the valence electrons in the VB to be excited into the CB, right? So as a result, you're going to have a thermal excitation. Okay, saya tak boleh tulis sebab saya tak bawa stylus ni. So it's called thermal excitation. So that means the valence electrons in the valence band are excited into the conduction band due to the thermal excitation from the increase of temperature, which is now no longer at 0 Kelvin. Okay, it can be 50 Kelvin, say 100 Kelvin, 150, 200, right, depending on the temperature. And you're going to have more and more valence electrons to be excited into the conduction band when you increase the temperature, right? So we're going to learn we're going to see how much of them and how the distribution of the electrons look like as you increase temperature in more detail later on. So another concept that you will learn in this topic is called direct and indirect band gaps. So have you learned this concept before at all? Perhaps in 307 or in other previous courses? Dah belajar ke? Direct and indirect band gaps? Anyone? Ada yang dah belajar? Did you learn in 307 band gap, direct and indirect band gaps? Should be, right? Yeah? Ada, okay, right. So you know already, right? Pretty much. So let's just recap the concept. Let's just revisit the concept. So what are direct and indirect band gaps? So when we discuss about electron movement in a solid, we assume that the lattice is periodic in nature, and then we assume that the electron motion to be a plane wave propagating through the lattice with propagation constant k, which is the wave vector. Okay, ini sama macam tadi. So in a semiconductor, if the values are in the CB where k is a minimum value or local minimum, okay, we're going to see the diagram later on, don't worry about it yet. In the semiconductor, if the values in the CB, in the band, where k is a minimum value or local minimum like U-shape kind of thing, when it exactly lines up with the maximum value or local maximum in the VB, so in the CB is like that, and you have a local minimum, and then in the VB is the inverse of U, and you have a local maximum. If the local minimum and the local maximum is perfectly aligned, then the semiconductor is said to be a direct bandgap semiconductor. Okay. In a direct bandgap semiconductor, there's no change of electron momentum is required in order to have a transition from the VB to the CB. Okay, for example, so in this particular case, it is quite clear that the local minimum in the upper part, so the local minimum will be there, right there, the minimum point, is not in a good alignment with, it's not aligned at all with the local maximum in the VB, right? So this minimum point there is not at the same K value with the same with the local minimum, local maximum in the VB. So in this case, you can tell right away that this semiconductor is direct or indirect? Direct or indirect bandgap based on your previous knowledge. In this particular case, indirect, right? So it's indirect because your local minimum here is not at the same K value, x-axis, as the local maximum, and therefore the semiconductor is indirect bandgap semiconductor, right? So indirect bandgap simply means that for your valence electrons in the valence band to be excited to go into the conduction band or to have a transition into this conduction band CB, it doesn't only have to have the right energy between the band gap for the band gap, but it also have to have the right crystal momentum, the K, the K value. So the Y has to be correct, the X has to be correct in order for the valence electron to have a transition from here to there. So that makes the transition is more difficult if you compare to direct band gap, where this minimum here, maximum here is well aligned. So that means your inverse, your VB here should be like that, right down here, and your maximum will be right below the local minimum. And at that point, it's considered as direct bandgap. And the transition, for the transition to occur, the valence electrons only need to have the right amount of energy in order for it to be excited into the CB. So there's no requirement in terms of the K value for it to be excited into the CB. So the transition from the VB to CB is a lot easier in direct bandgap. Bila sebut indirect tu macam combine kan. The transition is a lot easier from VB to CB in direct bandgap. Saya pause so that you're not confused. Indirect or indirect, to close, right? It's pretty close. So in direct bandgap material, where you have a perfect alignment of the K, it's a lot easier to have the transition from VB to CB. And the same goes to the reverse transition from CB to VB. You're going to see later on. And it's a lot more difficult for indirect bandgap, one word, for the valence electrons to have transition from VB to CB because of the K factor there that is required to enable the transition, right? So is it okay? Is it understood? Direct and indirect? Yeah, is it all right? So let's just go through this elaboration if you don't get it yet. So for direct bandgap transitions, where your local minimum and your local maximum is aligned at the K value, right? Direct bandgap. The energy loss, okay, this is talking about the reverse transition, right? So the transition can happen from valence to conduction band, maknanya dia naik, energy naik. So it has to be supplied with the right amount of energy for it to have a transition from VB to CB. On the other hand, the transition may also occur in the reverse situation. So that means the electrons in the CB may also go back to the VB, and in this condition, the energy lost. Tadi the energy gain then you go up. Now energy loss, that means transition is reversed, it goes down. And then bila it goes down due to the conservation of energy, the energy has to be released with the same amount of energy that is equal to the band gap if the transition is direct, right? And in this case, the energy loss in the transition can be given off as EG equals to the band gap, and it's equal to the amount of energy lah, right? Electromagnetic radiation in the visible, near visible range. So if you're talking about direct band gap transition from CB to VB, the energy lost due to that transition will be given off as photons. Okay, energy will be given off as photon emissions. In that case, for direct bandgap semiconductor, bila electrons drop from CB to VB, you're going to have light emission. So this is where you manipulate the semiconductors to become what? What are the example of the devices that emits light? What are the example of the devices that emit lights? LEDs, lasers, apalagi whatever like emit light. So this is the very physics concept that you want to understand. So it boils down to the transition between transition of electrons between CB to VB in direct bandgap semiconductor material. Okay, clear, right? LEDs, lasers, and so on, right? On the other hand, if you talk about indirect bandgap, yang tadi, yang this case, indirect bandgap, and for your information, this indirect bandgap is silicon. Crystalline silicon has indirect bandgap, just like this, 1.12. The separation between the EG is 1.12, but then for a transition to take place in crystalline silicon, you have to have the K factor there in the equation to be able to enable the transition. But that is not required in cadmium telluride, gallium nitride, indium phosphide, gallium arsenide, and that's why you see those materials with direct bandgap are exploited in optoelectronic applications, but not silicon. Silicon can, but under other conditions, right? Boleh, tapi you have to do something to the crystalline silicon to be able to change from indirect bandgap to direct bandgap. Then only it can emit light. Then only it can, but under normal condition it cannot, right? So in direct bandgap transition, assistance is required for the electron to change them. And for example, from an intermediate defect state or trap, for example, and the energy is lost is generally given up as heat to the lattice. So if you talk about transition of electrons from VB to CB for crystalline silicon, so it has to have the right amount of energy, Eg plus this component on the X for the electrons to have transition from here to there. And the same goes to the reverse process. You have to have resistance for the electrons to drop from CB to VB. And while for direct bandgap, your energy is lost as light or photon emission, which can be exploited for opto applications. For indirect bandgap, the heat is lost, the energy is lost as heat, and the heat is given up to the lattice. The lattice heating, right? So there's no light emission, but rather there'll be heat distributed to the lattice as a result of that transition, right? So therefore, generally for optical application, direct bandgap semiconductors are the materials of choice. The question is, if you know, if you already know some conditions, is there any condition for silicon to be exploited in optoelectronics? Or is there any condition where you can exploit silicon to emit light during the transition from CB to VB? Anyone knows? If you already have some ideas on that. Macam mana kita nak convert silicon with indirect bandgap to direct bandgap so that the silicon can emit light as well? Boleh ke? Is it possible? What do you think? Dope? Not quite. You can alter the conductivity, but then it's still direct bandgap in nature. Indirect bandgap in nature. So other possibilities? We have about 7 minutes or so. Any ideas? Okay, I wanted to explore this. I'll just give you a keyword and then you go back and search for yourself. You can do that for silicon if you can convert the crystalline silicon into silicon quantum dots. Why quantum dots? Any ideas from your quantum mechanics? Kalau quantum dots, how come it can emit light? Is there any relationship that you can explore? So I'll leave you with that to explore, right? So you can, but you have to convert the silicon into quantum dots, right? You have to introduce confinement to the silicon in order for it to behave like the right band gap. Okay, and you explore yourself. So that's the keyword given. Right. So this is just the illustration of the discussion just now in terms of the direct transition and indirect transition. So you can see on the left, it's like crystalline silicon with indirect transition, where you need to have the assistance on the x-axis in order to enable the transition. On the other hand, for the right band gap, like gallium arsenide, gallium nitride, cadmium telluride, and whatnot, there's no assistance required. It's just a vertical transition completely, right? So this is just another example as well. You can see here an example of silicon on the left, right, the indirect band gap, and then gallium arsenide on the right, direct band gap. Okay, sama. So let me just see conduction of carriers. Let me just finish off conduction of carriers, and then we can continue next week. So conduction of carriers. We have discussed already about the concept of partially filled and completely filled bands, right? For metals with two possibilities, and then semiconductor is in the middle. One EV is close to silicon, if you like, and then insulators on the far right, non-EV. So you're going to have enormous variation in electrical conductivity of metals, semiconductors, and insulators, right? So the explanation can be understood as below. For example, metal. So very low value of resistivity and a CB that is either partially filled or overlap. We've discussed this one in the previous few slides, right? So there's a band overlap generally between VB and CB, but you have exemption for sodium and potassium now. And uppermost electrons in the partially filled band or electrons at the top of the VB can move to a higher energy level available. So then they can available energy level when they gain kinetic energy, for example, from an applied electric field, if there is an applied electric field, right? So, but you can also leave it without the presence of electric field as well. So electrons are free to move with only a small amount of electric field in the metal because there are many unoccupied states close to the occupied energy states. Therefore, current conduction can readily occur. So it's very straightforward in metal. For insulators, it's the complete opposite because your band is your band gap is very big. So say in the region of 5 above, and you need a massive amount of energy in order to excite the valence electrons into the conduction band, right? Large band gap, note that electrons occupy all energy levels in the VB and all energy levels in the CB are empty. Thermal energy or energy of an electric field is insufficient. You just need a very big amount of energy to raise the VB electrons into the CB, okay? Even though it has many vacant states in the CV, the energy is just too big for it to have a transition, and therefore the insulators cannot conduct current, right? On the other hand, for semiconductors, it stays in between, right? At T0 Kelvin, as we discussed in the previous slides, all electrons are in the VB and there's no free electrons in the CB, and thus semiconductors are poor conductors at low temperatures, 0 Kelvin. It's almost frozen, if you like, right? So at room temperature and under normal condition, say around 300 Kelvin, values of Eg are about 1.12 for silicon, 1.4 for gallium arsenide, and at room temperature, the thermal energy KT is already sufficient to induce formation of free electrons or to thermally excite VB to CB, and this is caused by the thermal excitation. So if you've watched the video I posted in the group and on Elan, you can see the guy where they introduce heat, right? The massive heat to the silicon wafer. Then only the silicon conducts and then the LED lights up. on the other hand, bila dia turn off ataupun dia tak off lagi the thermal component tu, api tu dia then the silicon doesn't conduct and the LED is in off state, right? So this is the very same situation as explained here. It's due to the thermal excitation. So if you have watched the video, do you have any idea why bila dia tutup, kenapa when it turn off the api tu, dia off api tu, then the conduction stops? Why do you think, or what do you think is happening there? Kenapa the silicon conduction stops and the LED turns to off state? Any idea? Kenapa bila dia remove the heat source, api tu, then the conduction stops and then the LED turns off again? Okay, let's see your comment. Energy required for electron to excite is gone. Okay, energy is gone. Okay, energy is gone, but you supplied the energy and then the electrons are excited to the CB and then the silicon conducts and then the LED and the circuit is completed and the LED is on, right? Now, okay, he said, Zuki said, electrons recombine with holes. Okay, electrons recombine with holes. Electrons losing energy. Okay, patient electron fall back CB to VB. Okay, good. So the actual thing that's happening is when you excite the electrons from the VB to CB by using the heat source in that particular video, so the electrons are excited because the energy supply is more than what is required, which is the EG. So they are all excited. Then the circuit is completed. Silicon conducts, circuit is completed, and the LED is on. So the moment the heat source is removed, what happens is when you supply the energy to the silicon, some of the energy supply, we don't know for sure because there's no measurement to be exact. The energy supply could be more than what is required. So that means if the silicon needs 1.12, the energy supplied by that particular source could be 1.6, for example. Or it could be a range of energies depending on many conditions dekat yang di-supply tu lah kan. Dekat ke jauh ke all the stuff. When electrons are excited, if they're excited with the energy more than 1.12, they will be excited far into the CB. So not only at the CB edge. So for the conduction to happen, the electrons have to be at least excited to the edge of the CB. Mana dia jump sampai just right at the CB and conduction takes place. But in some of the conditions, some electrons are excited far into the CB. So that means, say it received 1.6 and it will go far into the CB, and then it will drop back to the CB edge. After you don't realize it, if you blink an eye, your eyes, that is already long enough for that transition to happen. So this process, when the electrons drop from the highest states in the CB into the CB edge and eventually recombine with holes in the VB, is called thermalization process. Okay, it's called thermalization process. So that means they're excited into the CB and then it thermalizes, or they thermalize back into the CBH. When dia naik atas, when dia jatuh balik ke bawah dekat CBH, eventually they will recombine with hole in the VB. And then this moment when you see the thermalization takes place, at that point you can see that the LED turns off again because the energy is no longer there, right? The energy is no longer there. So yep, so it's true that you said recombination, it drops back to recombine with holes and no more conduction. It falls back, right? And the process name is called thermalization process. Okay, where the excited electron drops back to the conduction band edge after some time. It's probably in the region of femtosecond or so, right? Depending on the system, and then it eventually drops back and recombines with holes. Okay, so this process is called thermalization followed by recombination. Okay. Recombination, nanti kita akan cover recombination and generation electron. So let's just stop here. We'll cover temperature dependence in our class next week and followed by our next topic. All right. So is it okay for now?
Yes, doctor.
So all clear? Cool. Everyone can follow now. All good? Good then. So if that's the case, then I'll see you again next week. Bye-bye. Take care. Assalamualaikum. Safe.
Bye, doctor.
Yeah, have a nice day. The keyword just now is called thermalization. Let me just write it down here. Thermalization, right? Thermalization. Okay.